So you guys have made it to the chapter 15 questions. Let's get right into it. So this first question asks us about the rate determining step of the nitration of benzene. So the important part here to note is that we're looking for the rate determining step of an EAS reaction. EAS just stands for electrophilic aromatic substitution. And if we pull up the mechanism right quick, we can see that the rate determining step is going to be the one where benzene is going to attack the electrophile, add a group to the benzene ring, and form the rhenium ion. So one more time, rate determining step is the step in which benzene attacks and performs an addition reaction, adding our substituent to the benzene ring. This is where we lose aromaticity and we create the rhenium ion. So going back to our question, the rate determining step would be not the protonation of nitric acid. Sulfuric acid, what's that even about? Loss of water to produce nitronium ion, that doesn't make any sense. Addition of the nitronium ion to produce the rhenium ion, that sounds really good. Loss of the proton by the rhenium ion, no, that doesn't make any sense according to our logic. So D is our correct answer. The second question, again, is looking for the rate determining step in the sulfonation of benzene. So same exact question, just now we're looking for sulfonation. This is still an EAS reaction. So again, we're going to use the same idea as we had before. So we know that the formation of SO3 and the protonation of SO3 don't make any sense. We're looking for the rhenium ion or the loss of aromaticity. Answer choice C says the addition of SO3 to form the rhenium ion. That looks good. Loss of a proton from a rhenium ion. Nope, that doesn't make any sense. So our answer is going to be C. Question number 3 is more of the same. And we already know if we're looking for the rate determining step, you are going to look for the formation of the rhenium ion, and we can see that right here in answer choice C. If you go through, you will see that none of the other answer choices make sense, so C has to be our answer. So now we are going to do some resonance questions, and I want you guys to reference this page that we did in SI and during the review session. It basically just goes through all the resonance structures for our activators and deactivators, and I just want to focus on this middle one really quick. So we know that when we have bromine as a group on our ring, aka a substituent, it's going to donate electrons into the ring, which will then cause the resonance to go around the ring as is drawn here. So one thing I want you guys to note is we will have a plus charge here as we make a double bond to our ring. In addition, we will have a negative charge that will be placed on the ortho and para positions across the ring. So just keep this in mind as we go on to our questions. So this first one, number 4, is basically asking us which of the following structures contribute to the resonance hybrid. So it's basically asking you for all of the possible resonance structures. And I want you guys to be careful, because if you don't read it thoroughly, you won't see that it says when bromobenzene undergoes parachlorination. So it is asking you essentially to show all of the resonance structures for bromobenzene. And as we said before, the resonance structures will start out with electrons from the bromine going into the ring, and then electrons will go all around the ring. So one thing I want you guys to note that's not necessarily very clear in the way that we drew out resonance structures before, is that sometimes instead of drawing this double bond here, we are just going to go ahead and show a positive charge on the carbon, and we're going to put those electrons back on the bromine. That's just another way we can express it, because it's more stable in this case to have the plus charge on the carbon rather than on the bromine. So we know that when we do resonance, all of these are actually going to be possible structures for the chlorination of bromobenzene. And we know that because once it becomes chlorinated, we will have a plus charge on either of the meta positions. We could also have the double bonded bromine with the plus charge. Or the new information that I just gave you guys, we can also express it as a plus charge on the carbon on which the bromine has been bonded. So our correct answer here would be E, all of the above. The next one, number 5, is slightly different. So again, it's asking for all of the following that are going to apply to the hybrid. And now we're doing chlorobenzene undergoing a chlorination. So the only thing that's actually changed is we replaced the bromine with a chlorine, and all of the exact same rules will apply. The resonance structure will be exactly the same. So once again, all of these are correct answer choices because they all contribute to the resonance hybrid of chlorobenzene once it undergoes parachlorination. Moving on to number 7. Number 7's slightly spicy because now we have an NH2 instead of a bromine or a chlorine. Again, this is asking for all of the following contributors. And I will just highlight parachlorination. But now it's saying exceptionally stable. So it's not just saying which one is possible, it's saying which of the following is the most stable. So in this case, the most stable structure is actually going to be based on where the plus charge is located. So we can see in 1, 3, and 4, the plus charge is on a carbon. Here on number 2, the plus charge is on the nitrogen. As we've learned before, our heteroatoms, such as nitrogen and oxygen, are going to be exceptionally good at holding a charge, much better than carbon is. So for that reason, answer choice B is correct, and resonance structure number 2 is going to be the most stable resonance structure. For number 8, we're going to use kind of the same idea, except now our substituent is no longer a nitrogen group, it's a methyl. And so in this example, it's saying which will be a relatively stable contributor, so it's asking us for the most stable resonance structure when toluene undergoes bromination. So now it's a little bit different because we know that even though the toluene will be an activating benzene structure, it is no longer going to be donating electrons through resonance. It's not really a crazy different idea if you understand where the positive charge is more stable and things like that, but I just do want to point out that the toluene will not be donating electrons through resonance. It will be through inductive effect. felt like I blabbered a little bit there, but I hope you guys get what I'm trying to say. So in this question, let's again look at the position of these plus charges. So we can see that these two structures are essentially exactly the same. The plus charge is meta to the methyl group. It's on a carbon, and we have these two double bonds in conjugation. We then have this plus charge, which is on the bromine, and the bromine is double bonded. And we said earlier that even though the plus charge is super stable on oxygen or nitrogen, it's actually less stable when it's on the bromine. So we don't like this answer choice. And we said that these two are exactly the same, so we can't pick one over the other. So we're going to cancel them out. Now, we have one plus charge that is on the carbon where the bromine is attached, and the other one is on the carbon where the methyl group is attached. And so now if we just kind of use our basic knowledge of carbocations, we can tell that the more stable carbocation will be on the more substituted position. In this case, our most substituted position between number 2 and number 3 will be number 3, and that is because this is a tertiary carbocation. This is a secondary carbocation. So C is our correct answer because 3 is the most stable resonance structure. I know that was kind of a lot. So let's take a break from resonance for a second. So we have a concept question. The electrophilic bromination or chlorination of benzene, aka this is an EAS, and we know it's a halogenation. And it's saying it requires what in addition to the halogen? So we know that EAS reactions are going to require some kind of catalyst because benzene is typically unreactive. And we know that we're usually either going to use an acid or a base in Orgo-2 in our reactions. So we can narrow it down to a Lewis acid or a Lewis base. Now, between the acid and the base, we learned earlier that we must have a Lewis acid in order to do our electrophilic aromatic substitutions. Specifically for halogenations, we are going to need something that looks like so. So that will be our Lewis acid. Next up, another concept, but this one is specifically about Friedel-Crafts. So just as a reminder before we do this question, we know that Friedel-Crafts cannot happen with NH2 or a strong deactivator. I know that's really sloppy, but I'll read it out loud. Cannot happen with NH2 or a strong deactivator. So here we're asking for which will be unsuitable as an inert solvent. So this is kind of like a double negative. Inert solvent just means it will be there and nothing will happen. And unsuitable as an inert solvent just means we're looking for a answer choice that will react with Friedel-Crafts. Will react. So we're looking for something that is not an NH2 and is not a strong deactivator. So we know that nitrobenzene is going to be a strong deactivator. We know that acetophenone is a strong deactivator. We know that trifluoromethylbenzene is also a strong deactivator. Chlorobenzene is a weak deactivator, and we know that Friedel-Crafts can happen with a weak deactivator, so A is our correct answer. For number 15, it's another concept question, and it's asking for polysubstitution, specifically undesired polysubstitution. So we know that this is going to only happen in the case of Friedel-Crafts alkylation. Next up, the question states, this substituent deactivates the benzene ring, towards electrophilic substitutions, but directs the incoming groups to the ortho-para positions. So we are looking for an ortho-para director that is a deactivator. We know the only ortho-para deactivators are going to be our halogens. So between these answer choices, the only halogen is C, and that is our correct answer. Number 17, this molecule does not normally participate in Friedel-Crafts reactions. So we're going to look for either a strong deactivator or NH2. Regular old benzene, that's out. Chlorobenzene, we know that's going to work because it's a weak deactivator. Nitrobenzene, yeah, that's a strong deactivator. That's a good choice. Toluene, that's just methylbenzene. That's an activator. Tert-butylbenzene, that's another R group. That is also an activator. So in this case, C, nitrobenzene, will not react in a Friedel-Crafts reaction. This next question is very similar, and it's just asking essentially the opposite. Which one of these can be reacted with Friedel-Crafts? So this next one is essentially asking for the opposite. So we're asking for which one can be used in a Friedel-Crafts reaction. So aniline is a benzene with NH2. We know that won't work. Nitrobenzene has an NO2. That won't work. Chloro, we know chlorine will work on a benzene ring, but please pay attention. Chloroethene, that will not work. That's not an electrophilic aromatic substitution. Bromobenzene, okay, that can work. Para-bromo-nitrobenzene. The bromo part of that will work. The nitro part of that will not. So the only one that makes sense here is D-bromobenzene. For number 29, we actually have two substituents on the ring, and we want to do another substitution reaction. So we're going to go ahead and pick between NH2 and chlorine to see which one is the strongest activator. We know that chlorine is an ortho-para director, and it's a weak deactivator. We also know that NH2 is an ortho-para director, and it is an activator, and this is actually the strongest activator we will be using in this class. So we know that NH2 is going to be the director, and since it directs ortho-para, we're going to direct the bromination to the carbons that I have drawn an arrow to. Now, please be very careful, and please take note of this setup. So if we have a benzene ring that has NH2 on it, and we react it with Br2 and H2O, in this case, we're actually going to get multiple substitution. So we're going to have multiple sub of bromine. So we're going to add multiple bromine groups to the ring. In this case, we have two spots where bromine wants to add, so we're actually going to fill up both of those spots. Before we even do that, though, we can kick off some silly answer choices. So right here, they moved the chlorine and nitrogen. They're no longer para to one another. That's out. Same thing happened. No, that was the only one where they did that. Sorry, I got confused. So, that one is out. We don't like answer choice A. Next up, we have number 3, and we're going to add the bromine ortho to the chlorine. That doesn't make any sense because our director is NH2. That's out. Here, one of them added ortho, one of them added meta. That doesn't make any sense. So now we're between 2 and 4, and this is where people get confused because it seems like this should be the correct answer. However, remember, in a case where we have NH2 on the ring and we react with Br2 and H2O, we are actually going to substitute multiple times. So the correct answer will be answer choice B. So this is my favorite question from this chapter because it's actually very simple, but students will get it wrong all the time, and hopefully once you watch this, you will not get it wrong. So the question is asking you, which of the following reactions would give the products indicated in a substantial amount, which is greater than 50%. So what this is asking you for is major products. Major products. So, number 1, NH2 with a Friedel-Crafts. We know that that's not going to happen. No reaction. NH2 with Friedel-Crafts. Again, not going to happen. No reaction. Now, this last one, students will say, cool, that one works because it's a Friedel-Crafts and there's nothing on the benzene ring. But one thing I want you to note is that this is the alkyl halide we have, and it's going to turn into this carbocation. And in this example that they gave you, this answer choice rather, they added the carbocation as is. But we know that this carbocation can actually undergo a rearrangement, become secondary, and then add to the benzene ring like this. And we know between these two, the major product will be this guy because we want to undergo a rearrangement and we want to get the more stable carbocation. So this is not going to be correct as drawn because this is giving you the minor product. So the answer for this question is E, none of the above. Ta-da!